So last time we finished up this example to find the vertical and horizontal deflections at the free end of this quarter circle cantilever. And so for the vertical deflection, remember we didn't have to add a fictitious force because we have a vertical force in reality at that location. And then we solved for that deflection. Since it was a positive result, that tells us it's in the same direction as the force that we used. And then for the horizontal displacement, we had to add a fictitious force there. And so we do the whole process again with respect to that fictitious force, which involves eliminating that fake force after we've set up the integral. And then we found the result acting in the same direction again as the fictitious force. So summarized with a few comments here, and then I have a few more comments related to this example as well. So I'll continue that on the next page. All right, so first, if we consider the configuration, right, we can expect that the bending or the internal moment will be greatest at the fixed support, right? So we know what that maximum moment would be, or we can calculate it now. Actually, we could have calculated it right at the beginning, right? Since it is a determinate structure. So that moment would be negative PR times sine of phi. That's the distribution. And at the fixed end, phi is pi over 2. So for total bending stress, we would still want to include the effects of any normal force. Right, even though we neglected it for the purpose of strain energy, we still have it contributing to bending stress. And then also keep in mind that with this energy method, we only obtain the deflections at the corresponding loads that we're using, right? We don't obtain the distribution of deflections. Once we have let's see, what do I want to think about here? So if we have, for a determinate problem, right, we can easily obtain the moment distribution equation. So we can derive the formula for deflections from that, right, using the same methods that we've used before. If it's an indeterminate problem, then we need to use that deflection approach if we're using this energy method to find the reactions. Once we know the reactions, then we can obtain the moment distribution and then derive the deflection distribution from that if we want to. We're not going to take these problems that far in this class, but just as FYI, you could go there. So I'll just note with this method, we only obtain the deflections at corresponding loads. And it doesn't matter if they're real or fake. And then the last point, for indeterminate structures, the deflection calc is necessary. Oops. All right, so the example we just did was determinate. We didn't have to do that part. But in the next lecture, we'll look at indeterminate configurations of circular beams specifically and apply this method. But first, we have another couple of determinate examples. So what do we do if we have a distributed load on a structure and we want to use this method? So first we'll consider this quarter cantilever circle with a uniform pressure load. All right, so the pressure load suggests, and is confirmed by the drawing here, that the loading is transverse or perpendicular to the circle, right? If we want to find the vertical deflection at B, we still need to add a fictitious point load there in order to make this work. So if we take a cut then and look to the right of that cut, now with our fictitious force involved, we expose the internal shear, normal force, and moment. What we're interested in is the moment. And before we sum moments to get that distribution, I'm going to break down this pressure load into the horizontal and vertical components. So the horizontal component I will sketch as acting over that vertical projection of this portion of the circle. And this distance, which is also the moment arm about that cut location with respect to the applied load at the free end. No, that's not true, because that moment arm would be the horizontal distance. But this will come into play. All right, so this distance is r times 1 minus cosine phi, similar to what we had before in the other example. And then we would have the vertical component of that force acting over the horizontal projection of the portion of the circle that we're looking at here. And this distance would be that moment arm for Fi r sine of phi. Phi, not theta. Okay. So having broken that down, we sum moments about the cut. So we get 0 is equal to the moment distribution, or this is m of x, right, to be clear, plus, or actually this is going to be in terms of phi, not x, right? So m of phi. All right, and then we have the fictitious force times its moment arm, r sine phi, plus the horizontal component. So the resultant of that would be q times r 1 minus cosine phi. All right, so that's just the pressure load times the distance over which it acts. And then the moment arm for that resultant is 1/2 times R1 minus cosine phi. So this part is the QX resultant. And this is its moment arm. And then we also have the vertical component of Q. So QY will be Q times R sine phi. And that moment arm will be R sine phi over 2. So this simplifies then down to, let's see, how do I want to do this? I'm going to say this part in green underline simplifies to QR squared times 2 minus 2 cosine phi. That won't be immediately obvious, but that's what it simplifies to. So we can then write M, as it varies with phi, is equal to negative QR squared times 1 minus cosine phi. Let's see, and I missed something over here. So it's QR squared over 2 on that green line is what this simplifies to. So then we bring that over to here, negative QR squared times 1 minus cosine phi, and then we have minus Fi R sine phi. All right. So then we set up our integral for calculating the deflection at B. So we have the partial derivative of strain energy with respect to the fake point load. And that's equal to 1 over EI times the integral from 0 to pi over 2 of our moment equation. So negative QR squared times 1 minus cosine phi minus Fi R sine phi. And then the partial derivative of that moment expression with respect to Fi, which is just negative R sine phi. And then we have R d phi. Now that we have set that up, we get rid of the Fi R sine phi term. And this becomes, when we bring out constants to the front, QR to the 4th over EI times the integral from 0 to pi over 2 of 1 minus cosine phi times sine phi. And evaluating that integral, we get QR to the 4th over 2EI. All right, so before I gave you guys a trig identity, I think I did. Oh, I gave you guys a couple of trig identities, but in the previous example, we had the integral of sine phi minus sine phi cosine phi. So that's the same thing that we have here, right? Just written slightly differently. All right, any questions? I'm gonna fix that too. So at first glance, this problem with the uniform pressure load on the quarter circle might appear to be simpler than this problem, right, where the pressure load is just vertical. But it actually is going to be simpler in this scenario with the vertical only pressure. So this would be the case if we had, for example, a snow load. And generally, and those of you that took my structures class will remember this, snow loads tend to have roughly uniform depths, or the depth of the snow is roughly uniform over the roof, regardless of how it's shaped, assuming the wind hasn't caused things to drift and move around, right? So the depth of that distribution will be the same on this end as it is on this end, right? So it's a constant vertical load distributed over the horizontal projection of this arc. So if we then were to take a cut and break everything down, we only have the r sine phi component now. All right, so if we sum moments about the cut, we have 0 is equal to m plus qr sine phi times the moment arm of r sine phi over 2 plus fi sine phi. So m is equal to negative qr squared over 2 sine squared phi minus fi r sine phi. A lot simpler. The deflection equation then would be 1 over EI times the integral from 0 to pi over 2 of negative QR squared over 2 sine squared phi minus Fi r sine phi. And the partial derivative, again, is negative r sine phi. And then we have the r d phi, getting rid of the Fi term now. We evaluate that integral. It's going to be, well, we'll simplify it first. QR to the 4th over 2EI times the integral from 0 to pi over 2 of sine cubed phi. All right, so here's another trig identity for you. The integral of sine cubed phi is negative 1/3 cosine phi times the quantity 2 plus sine squared phi. Or you might just want to use your calculator. So our delta by would come out to be 1/3 QR to the 4th over EI. So comparing those two, we had QR to the 4th over 2EI for the uniform pressure, and now it's QR to the 4th over 3EI for only vertical pressure. So a little bit different, assuming you have the same magnitude, if it's vertical versus perfectly transverse. Right? Yeah.
Remind me why we drew the FY term in the integral? Is that just because it's imaginary?
Yeah, because it doesn't exist. Yeah, so we only we only use it to set up the integral, and we just need it for that partial derivative component. Yeah. All right. So now we're ready to dive into statically indeterminate circular beams. So that's beginning the next lecture. And I think, let's see, I know we won't get through the whole lecture, but I think we will get through, we'll definitely get through the first example. And so maybe what I'll do is post a recording of the second example, so that we'll be back on track, if that sounds good to you guys. And then I can spend some time in class, kind of briefly talking over it instead of working through the whole thing. Does that sound okay? All right, so for a statically indeterminate circular beam, procedure is similar for statically indeterminate straight beam. We would remove the support constraint or constraints until they're statically determinate. And a light bulb just went off in my head too, because I remember last time, Bryce, was it you or someone asked, maybe it was Cash or Will, I don't remember, someone asked, how do you do it if you have more than 1 degree statically indeterminate structure? So it's actually simpler than what I was thinking. All you do is you would remove however many constraints you need to make it determinate, and so you would treat all of those constraints as applied loads, but then you would have to do all 3 deflection equations to get through and solve them, right? So you'd have to kind of treat them one at a time and then use superposition, yeah. And then second, then place forces at those released constraints and impose displacement conditions to determine those unknown forces. And then derive the moment distribution. And then from there, you would proceed with the energy setup. So this first example is, let's see. Yeah, so this first example is going to be the more complicated one of the 2 examples in this lecture. So it'll be good to do this one in class for sure. We're looking at a half ring that is 1 degree indeterminate, right? So it's pinned at both ends. And we have the radial pressure loading. So again, this is the radial pressure loading where it's perfectly perpendicular to the curved beam. In this scenario, what makes this case more complicated is that we can't ignore the axial contribution to strain energy in this situation. So the combination of the indeterminate configuration and the radial pressure means that there's going to be significant axial energy involved, and so we have to include that in our solution. So most cases we can ignore the axial component, right? So in the second example that's in this lecture, we can ignore the axial component, but for this particular case we can't. So I'll note that stuff here. It's 1 degree indeterminate. So the strategy that I'm going to take, right, we release 1 constraint to get it to determinate, you can pick any one of those 4 reactions to release. So I'm going to pick the horizontal reaction at C. So essentially, we're going to release the pin at C horizontally. And replace it with a constraint force. We'll call it FC. So I'll sketch that down here. All right, so this is then taking a cut and looking to the right of that cut. We have FC involved there. We also have our vertical reaction, we'll call that CY. And from statics, all right, even though it's indeterminate, because we have symmetry, we can tell right away what the vertical reactions are going to be, right? They're going to be equal in magnitude. And they're each going to be equal to half of the resultant vertical force. So in this case, it's QR. And then I'll make that note about the fact that we can't neglect the axial component. So we have radial pressure combined with indeterminate configuration. All right, so I'll continue marking on this sketch here. Taking a cut there, we expose the internal shear, normal, and moment. The resultant forces of the radial pressure, we have horizontally QR sine phi, and vertically we have QR times 1 minus cosine phi. So if we sum moments in the sum forces in the normal direction, we're going to obtain an expression for the internal normal force N with respect to Q and phi. So by normal direction, I just mean the direction that is consistent with the internal normal force at the cut. And that, of course, will vary with angle phi, right? So this is going to be a function of phi. So we have N plus FC sine phi and then we have the vertical reaction, CY, which is QR, but we want the normal component of that vertical reaction. So that is going to be QR times cosine of phi. And then we want the normal component of these two resultants. So that's going to be from the horizontal resultant, QR sine squared phi minus QR times 1 minus cosine phi times cosine phi. Ran out of room. And then solving for n, we get negative, it'll simplify a little bit, negative FC sine phi minus QR, and then that gets multiplied by a cosine phi, a sine squared, a negative cosine phi, and a positive cosine squared. So the cosines will cancel. And then using the trig identity for sine squared plus cosine squared, exactly, we get n is equal to negative FC sine phi minus QR. And then next we'll sum moments about the cut to get an expression for the internal moment. So we have 0 is equal to m, or that'll be negative m. I'm going to take positive counterclockwise, I guess. So negative m minus FC times r sine phi. So the r sine phi is your moment arm for the horizontal constraint. And then we have QR squared times 1 minus cosine phi. So that's your, let's see, QR squared. Yeah, so QR times 1 minus cosine phi is the resultant force, and then the moment arm is going to be, let's see. Oh no, sorry, this term is for the CY, right, which is QR, and then the moment arm for QR for this vertical force to this point is going to be R times 1 minus cosine phi, which is that distance. And then from the resultant forces in the vertical and horizontal directions, we're going to have, from the vertical resultant, negative QR squared over 2 times 1 minus cosine phi, and that quantity is squared for the moment arm. And then minus QR squared over 2 times sine squared phi from the horizontal resultant and its moment arm. So this is FC times its moment arm. This is, what did I say? That's the vertical component. All right, and that's the horizontal component. Times moment arm. All right, so final answer for moment, we get negative FC times R sine phi. So this is curious because there's no Q that shows up in that moment expression, right? But Q, of course, does contribute to the moment because that's going to be built into, right? Q will contribute to what FC is, right? All right, so again, for the total energy, we need to include both bending and axial components. And again, I will emphasize that normally we can neglect it, but not this time. All right, so our strain energy expression, 1 over 2 EI times the integral of m squared r d phi plus 1 over 2 AE for the axial energy times the integral of n squared r d phi All right, so once again, we can take advantage of symmetry at this point. Since we have a semicircle and symmetric supports and symmetric loading, we can just shorten our integral span. So we can integrate from 0 to pi over 2 and then double our answer to get the full effect, right? All right, so we're starting with the horizontal direction since that's the constraint we released. And we know that that displacement has to be 0 because in reality there is a support keeping it from moving horizontally. So we set that equal to 0 and write our expression from the strain energy formula. So 2R over EI times the integral from 0 to pi over 2 of FC r squared sine phi d phi. And then, let's see, what did I do here? So we have this, and then our FC, our normal force is here. All right, I'm gonna have to check on that. But, so we have negative F sine minus QR times, oh, okay. Right, okay, so I skipped a few steps already. All right, so that's fine. So this is, I'm trying to remember what I did. Okay, so we've got, here's from the moment, right? So FR sine phi, and then the partial derivative of that with respect to F is negative R sine phi. So the two negatives cancel out, so we have a positive. And then on the other side, we're going to end up with a net negative here. So it's going to be minus 2R over AE times the integral from 0 to pi over 2. And then we have our expression for n is negative FC sine phi minus QR. So that's negative FC sine phi minus QR. And then the partial derivative of that with respect to FC is negative sine phi. So that's why I just brought that negative sign out here. That's what was throwing me off. I was like, how did I get that negative sign? Okay, now I see it.
Is our n term not squared?
Oh, thank you for asking. So this is the original form for strain energy. The modified Castigliano's theorem, and I should go ahead and write this down to connect those dots. We, instead of squaring the m, we have m times the partial derivative of m with respect to the force, and similar for the n, right? So instead of m squared, we have m times the partial derivative of m with respect to, in this case, FC, and the partial derivative of n, or n times the partial derivative of n with respect to FC. So that's part of the modification of Castigliano's method, is replacing that second m and second m with the partial derivative. All right, so then solving for FC, we get negative 4qri over pi and ar squared plus I is all multiplied by pi in that denominator. So if we back substitute, we can solve for n in terms of the applied loading. So we get n is equal to negative qr plus 4q ri in the numerator. Denominator has the same, pi times quantity ar squared plus I. And then that's all multiplied by sine of phi. And the moment would then be 4 times q r squared I divided by the same denominator. And then that's also multiplied by sine phi. So the last step in this example is to plot the moment distribution from the fixed support to the free end. Actually, I take that back. This is plotted in the reverse. So we're taking phi as 0 as point C, right, the way I'm going to set it up. So this will be phi of 0, and we'll just plot it to pi over 2 since we know it's going to be symmetric from B to A. So we'll start this plot over here with this point representing C and this point representing B. And in order to plot this, because that doesn't look very fun, I'm going to make our lives a little bit easier and normalize that moment. So I'm going to define a lowercase j as qr squared I over AR squared plus I, so that M over J is equal to 4 over pi sine phi. And that's a lot more digestible to plot. So that comes out to, at pi over 4, you get a value of 0.9, and at pi over 2, a value of 1.27. So I'll make that a little bit higher. I'll change the color, green. And so that plot would look something like this. All right, and then it would be symmetric to pi. So a few quick comments, and then I know we'll be done. Of course, moment is equal to 0 at C, the free end, as it should be. And it builds to a maximum at point B, which is the center, right, of the arc, the top. And M, of course, should be 0 at A, which is the other pin support, which makes sense. Questions? Are circular beams fun? All right, well, the next example, like I said, I'll post a video and then just kind of talk through it briefly in class, see what questions you have. But the second example will be a little bit less complicated because we won't have to deal with the axial term, and you also won't have to deal with that axial term in your homework problems. So, but it's worth throwing it in there in class. It's, you know, got to make it a 400 level class somehow. All right. Well, thank you all for your attention. I'll see you Wednesday for the exam, and let me know if you have questions between now and then. I will not be on campus tomorrow, but you're welcome to email me, and I'll do my best to keep tabs on that.